Hi, I'm Matt Woodley, Solution Engineer on Esri's National Government Team. As a St. Louis resident, I'm your local Esri Solution Engineer. So if you see anything today that you would like more information on, or if you would like to work through a GIS problem with an Esri person, I'm your guy. As Tara alluded to, my colleague Chris and I are going to demonstrate the enhancements and workflows that make ArcGIS a complete imagery platform. To be a complete imagery platform, we must have these four key capabilities. Essentially, our goal is for you to be able to go from sensor to information product without ever leaving the ArcGIS platform. And with the newest releases, we set out with these three goals or categories in mind. Improving access to imagery by being able to pull it from where it lives, optimizing the storage, and adding analytic capabilities to the web tier. We also wanted to enhance processing with focus on speed and ease of use, and lastly, advanced 3D technology to create visualizations that are as stunning as they are informational. To see how we put this into action, we'll start in ArcGIS Pro. Our study area is going to be the Grand Ethiopian Renaissance Dam project. We're going to use imagery analysis to see if we can gain more insight into an international conflict. Ethiopia has constructed a massive hydroelectric dam on the Blue Nile River. Its neighbors, Sudan and Egypt, have relied on this water source for centuries and want to ensure the resources are shared equitably. Egypt have asked the international community to step in. The U.S. has threatened to withhold aid to Ethiopia if a legally binding agreement has not been reached prior to filling the reservoir. However, recent imagery indicates Ethiopia has operationalized the dam and begun filling its reservoir. Images are generally large files, and hard storage, while more affordable now, is still expensive. Many customers are turning to the cloud, where storage is inexpensive and scalable. We are going to conduct our analysis and pre-production workflows using imagery stored in the cloud. I have a few images from Planet Labs sitting in an S3 bucket that I want to use. Normally, I would have to download all these images to my machine first, but using a cloud storage connection, I can get to the imagery right where it lives. For my cloud storage connection, I need to give the service provider, in this case, which is Amazon. Then the S3 bucket name, you can see here, is Planet Imagery Grand Basin. Now I can also secure my S3 bucket by providing an access key and a secret access key. The region and service endpoint are going to be automatically filled when I attach it to the bucket. You can see here that I've created something called an ACS file. And this ACS file is acting as sort of a bridge from my file system to the cloud. Expanding the cloud connection file, we can see a list of folders and files that are in the S3 bucket. And you can also see that we're running into a pretty common imagery workflow snag. All of my images are buried deep within the delivery structure. And so I could search through each of these folders and add the images one by one. But instead of doing that, I'm going to use a mosaic dataset, which is an optimized storage solution. Creating a mosaic dataset is very straightforward. It's as simple as adding a new feature or a new dataset to my database. I'm going to call this new mosaic dataset the Grand Renaissance Dam. When creating a mosaic dataset, I actually have the option to assign it a product definition, which will automatically assign the band combinations and apply the metadata to one of our most common formats. However, this Planet Labs imagery is a unique case, so I'm going to leave this as none. It only took a few seconds to create this mosaic dataset. But again, I want to remind you that this is just a storage container. So we need to add our rasters to it. The cloud storage connection and the mosaic dataset make this pretty simple. All of the options that I can work with in this dataset are right here on this drop-down menu. And I can use the Add Rasters tool. With the Add Rasters tool, I have the ability to add a single file image, an entire dataset, or a folder. We can see here that the ACS file is acting as a gateway. And that gateway gives us access to the Grand Renaissance Dam imagery. After I hit run, the tool is going to crawl through each one of my folders, select the images that I need, and assemble my mosaic dataset. After the mosaic dataset is completed, I can confirm it contains all the images from my Esri bucket by opening the attribute table. Instead of working with all the images, I split them out into datasets for July 1st, prior to dam operation, and August 15th, approximately 1 month after operation began. Having my images in mosaic dataset allows me to work with them as a group instead of individual rasters. And so that means when I apply stretch types, or resample, or even apply band combinations, it's going to apply to the entire mosaic dataset rather than individual rasters. By adjusting the band combination to color infrared, I can distinguish between the water and the vegetation. And toggling off July 1st, I can see the massive environmental change caused by the operation of this dam. The mosaic dataset is great for managing your imagery and saving time by manipulating the images as a whole. But part of being an image analyst is doing some exploratory analysis. And for this, I'll use a raster function. Raster functions process the pixels directly rather than writing out a new raster to disk, saving me time and space. And I need to know if these images are worth exploring forward, so I'm going to run a compute change function. Compute change allows me to compare my mosaic data sets directly to each other and output a quantifiable measurement of change. As I mentioned before, this is writing a new layer directly to memory, and it's not writing anything out to my disk. At this extent, I can see that there has been massive change in the environment since the dam began operation. Based on the large swaths of dark purple and green, I definitely want to share this with my colleague, Chris. In ArcGIS Pro, since I am linked to the portal through my identity, I can share the mosaic dataset as an image service so Chris can exploit it in Excalibur. This allows me to collaborate with colleagues across the country without either one of us having to leave the ArcGIS platform. To prepare this as an image service, I need to provide a summary of the service, as well as some tags to make it discoverable by my colleagues. I also need to select the folder that I can store it in, and then make sure that I point it at my image server. Once it confirms that the image server is federated, I'll be able to analyze and publish this data set. And while that publishes, I'm going to send it over to Chris to continue our analysis on the web and Excalibur.
Thank you, Matt. Let's now take a look at how we can utilize that imagery in the web. Through ArcGIS Excalibur, we can take that same imagery that was just being used on the desktop, and we can explore it further in the web. As a web-based application that unifies imagery and geospatial data, Excalibur enables users to exploit imagery and conduct streamlined image analytics all within a web browser. Today, we will use it to explore that same imagery to gain a better understanding of the Grand Ethiopian Renaissance Dam and its characteristics. Within this project, we have the two images of the dam that were taken in July and August. The July image, which we are currently viewing, shows the dam is under development, as there is not much flooding leading up to it. While the later image shows a much larger floodplain just before the dam. To better visualize these images simultaneously, we can utilize the Flicker tool to quickly identify structural and environmental changes between the images. Here we clearly see that the image taken in July, the dam was not yet fully operational, as the Nile River is rather narrow and there is no spillway over the dam. While the image taken in August, on the other hand, shows the dam is indeed operating based on the active spillway as well as the substantial amount of water flowing beyond it. with water levels clearly covering many of the rock structures in the river. To better visualize the floodplain itself, we can quickly adjust the bands through the image display tools, where we can utilize the imagery's near-infrared band. Through this band combination, we can easily identify the areas within the image that contain water, as well as those that contain vegetation, giving us a clear visualization of the change in water level due to the dam's construction. Let's now create a report of our observation that can be shared with our organization. We can use the markup tools to quickly bring attention to the observables in the image. Once that is complete, we can generate a report. While generating the report, we can explain our observation in the Analyst comment section. Notice, the report automatically captures critical information, such as who created the report and when, as well as location information from the image. Let's now return to Excalibur and explore how it can be used for other workflows. Excalibur allows users to quickly navigate between projects and imagery collections without having to leave the application. And with a few clicks, I can be working in an entirely different canvas. Within this canvas, we have a collection of images that were taken over Tripoli, the capital of Libya, that we will utilize to create a structured observation management, or SOM project. Most of these images were taken throughout 2014, which is important because on July 14th of that year, the airport was the site of a fierce battle between militias as they each attempted to gain control of the airport. Reports stated that many of the airport's facilities, as well as airplanes, were damaged in the fighting. And today, we would like to explore this imagery collection and use it to conduct a SOM workflow on those damages. The first thing we want to do is isolate the images we need based on their coverage. And to do so, we can quickly filter the images by sketching an area of interest, which in this case is the airport itself. Now that we've filtered down to only the images that intersect our area of interest, let's select an image from before the July 14th attack and one from after, in order to identify damaged areas. Let's again utilize another one of Excalibur's display tools, this time the swipe tool, to visually assess the damage. As we pan around the airport, we can clearly identify damaged buildings as well as damaged airplanes. Let's now take these images we've selected and create a project by hitting Save. We are now ready to capture observations using the image that was taken just after the attack. And we have two options here. We can add observation feature layers that were previously created, or we can create new ones. In this case, let's add a few that have already been created. Here we have one for damaged aircraft and damaged infrastructure. As we return to our project, we can see the observations that have already been captured. Excalibur makes the process of collecting observations extremely simple. We select the observation we wish to capture, click its location, capture any necessary attribution, and submit. Although these observation feature layers were created for this type of workflow, their existence is not limited to Excalibur. In fact, they exist as items within my organization's portal. Items that I can share with members, as well as use to create web maps. Here's a web map that I created from the observations made in Excalibur. This web map can then in turn be extended back to users on the desktop, or be used to create a web application within my organization's portal. This ultimately demonstrates how versatile and integrated the ArcGIS platform truly is. And with that, I would like to now shift gears towards some of the new visualization capabilities within the ArcGIS platform. A new 3D visualization capability comes to ArcGIS Pro, and they are Voxels. Starting in version 2.6, Voxels enable users to view and interact with NetCDF data as 3D volumetric layers within a scene. NetCDF is a file format for storing multidimensional data, often where the X and Y values represent location and the Z value represents elevation or time. This data structure is useful for a number of communities. For geologists, they can use voxels for subsurface modeling, as well as understanding the distribution of soil types. Voxels are also useful for weather data, where the Z value can represent either a moment in time or a specific atmospheric condition. And finally, voxels can be used for creating and exploring space-time cubes. Let's take a look at a voxel now. Here we have an ArcGIS Pro project with the voxel layer representing long-term monthly precipitation averages across the entire world, with the X and Y values representing location and the Z values representing time, or in this case, months. To explore this type of data, we can use what is called slicing, which allows us to separate values along a given axis or dimension. And here, we can slice by the month to see how precipitation values vary from month to month. Let's take a look at the southeastern United States and see if we can use this voxel to identify the rainiest months of the year. As with other layers in ArcGIS Pro, we can adjust the symbology to meet our needs. In this case, let's reverse the color scheme to something more appropriate, where blue represents the highest amounts of precipitation. As we slice this voxel, we can see that June and July are the months that receive the most precipitation. Furthermore, we can use the transparency function to isolate values within the voxel layer. Let's now return to where our imagery adventure began, the Ethiopian Grand Renaissance Dam, and see what our voxel tells us about that region. From this analysis, we can discern that this region receives the most precipitation in the months of July and August. This information could prove very valuable with regards to how the dam operations must vary throughout the year. These are just a few examples of how users can view and interact with multidimensional data within ArcGIS Pro. I'll now hand it back over to you, Matt, to show us some of the other new visualization capabilities within the ArcGIS platform.
Thanks, Chris. Continuing on our theme of advancing 3D technology, I want to show you one of our newest offerings, SURE for ArcGIS. In defense and intel organizations, situational awareness is key to successful missions and operations. And to gain an advantage, we see many agencies turning towards these 3D mesh products as they provide unrivaled visualizations of mission planning simulation. We can create these realistic digital twins by combining photogrammetry and LiDAR together into point clouds, photo-textured 3D meshes, and true ortho photos. This data can then be leveraged as a reality capture from cityscapes to entire regions, so your simulations can be as accurate as possible. And by accurately processing these large extents and high volumes of images, you get a workflow that's as simple as you want and as advanced as you need. We acquired nFrames and the SURE product to meet these industry challenges. Data volumes are increasingly fast and complex, so we need software that can keep up. We also want to strive for highly accurate and sharply detailed imagery products to better model the built environment. Our customers are constantly being asked to do more with less. They do not have time to be waiting for images to render. And finally, the tech must be user-friendly so it is less of a hassle to become experienced. Let me show you what I mean by combining the SURE product with another desktop offering, ArcGIS Earth. Moving into ArcGIS Earth, we can view the show product as a 3D scene of Frankfurt, Germany. When panning and zooming, we can see that it renders quickly and the visualization is clear and sharp. It is more than just a fast rendering visualization though. The Sure product is actually an interactive layer that I can conduct analysis with. As a goodwill gesture to our hosts in Frankfurt, we have offered to provide security systems for the Christmas market. I need to understand the best vantage points to place our cameras. Instead of just guessing and running viewshed analysis on my camera locations once they're all placed, ArcGIS Earth allows me to place the camera interactively using the viewshed tool. So I place my first camera and adjust its rotation. I can see that the elevation provided by the 3D mesh is considered by the viewshed. And since it is so detailed that I can be sure to understand and know exactly what I can and cannot see and plan my locations accordingly. You've seen the Sure product on the desktop with ArcGIS Pro and ArcGIS Earth. But this being an Esri product, what we can process on the desktop can also be shared to the web. The Sure 3D mesh is optimized for this type of application. With this web-optimized 3D mesh of Erfurt, Germany, you get all the zooming, panning, and rotating 3D realism that you get on the desktop. Plus, the added benefit of near-instant rendering because of the server-side processing. Again, the 3D mesh in the web is more than just a pretty picture. Since this is a true 3D mesh, the objects are recognized as solid. I can get 3D measurements like base to top height that show in a heads-up display with just 2 clicks. With the heads-up display, I can view my measurements from any angle. For mission planning, I can adjust the sun angles so I can model how the shadows will play off the buildings and terrain. This allows me to understand what impact the time of day and the season of the year could have on my operation. I can choose today and turn on the shadows. Then, with a simple slider, I can model an entire day and change between seasons by selecting different months. By combining the Sure 3D mesh with the analytics built into the ArcGIS platform, I am able to prepare models for almost any situation, so I can be confident in the intelligence that I have gathered and the recommendations that I have made. We were able to go from sensor to analysis to product without ever leaving the ArcGIS platform. By leveraging the interconnectivity of the platform, we gain efficiencies in all phases of imagery collection and interpretation.